So we can start, and what we are dealing with, we are dealing with this BFS algorithms. Breadth first search, one of the fundamental searching algorithm for the graphs. Okay, that means given this node, say this is the S. Given this node is, we are trying to check whether I can reach to this guy, Y or not. Okay, or to this guy, or to this guy, whether we can reach from this source node. That is the main essence of this searching algorithms in graph. Okay. Now we have seen how we have to do this. Okay, and along the way, what we have seen other thing is that in terms of number of hops from the source to every other nodes, we are having the shortest path. Okay, using these BFS algorithms. Okay, so we are we are trying to, we are having this information that whether we can reach from S to this Y or U or T or whatever node, that information we are getting. Along with that, whether in terms of number of hops, the shortest paths are achieved or not, that also we have got. Okay. We have seen that we have got in terms of number of hops, we have got the shortest path. Okay. Now we can analyze this algorithm. Okay. So this is our breadth first. This is our BFS algorithm. Okay, and we have to analyze that what is the time complexity of this BFS. Okay, right. And whenever we talk about graph complexity, the algorithm complexity of any graph algorithms, we talk in terms of this V and D. Okay, you can think of V equal to N, E equal to M, E equal to M. Okay, so this order of V plus E in your familiar term will be boiling down to this. Okay, order of N plus M, right? So what what we will be doing, we will be having this aggregate analysis of amortization that we have learned earlier. Okay, so we use aggregate analysis that was discussed earlier. Okay, so in CLRS it is discussed in 17th chapter. Okay, so this is from CLRS. So now after initialization, what breadth first search is doing, breadth first search never whitens a vertex. So this you have seen that in this initialization process, what we are doing, we are whitening the vertices, all the vertices. Okay. So except the source node from where we have to explore. Okay. So from here, so all the vertices we are whitening. And from the source node, whenever I am trying to explore, okay, we have seen that in this in this area, it is not the case that, okay, say I have whitened all these guys, okay, and then whenever in this loop I am iterating, say this node is blackened, okay, this node is blackened, and we have never seen that whenever I am iterating this, that at some point of time, okay, no, I have done it wrongly, I will be making it white right now. So that thing we are not doing at all. Okay. So this is becoming again white. This is not done. Okay. So once for all, whatever I am doing, I am making it white. All the nodes, that is done for once only. Okay. In this iterating process, I am never say if it is gray, then in the next iteration I am making it white again. This never happens. Okay. That you got to understand. And thus the test. So we are making it white once. Thus the test in line 13. So that line 13, the testing, that whether this any node its color is white. Okay. The test in line 13 ensures that each vertex is enqueued at most once. Okay. So if it is white, then ultimately I'll be enqueuing that vertex. Okay. Are you getting? If it is white. So in this loop, if that node is grayed or that node is blackened, it will never be white. So that means what we are doing with that condition, that once for all we are making one node white, that having implication that only once a node can be enqueued. Okay. Only once throughout all the process. It will never be enqueued again. Okay. Right? So it is the similar in that stack operation. Okay. So once I am pushing it, when I am pushing one element into the stack, that will be popped up only at most once. Okay. That will be popped up at most once. So I am pushing and then I can pop it off once. It is not that case that I am pushing once and I will be popping that element 2 times. It is not the case. So it is the similar argument we are having here, that once a node is enqueued, that means we'll be giving the logic that it will be dequeued once. Okay. It is similar to that stack implementation of amortized analysis. Okay. And hence it is dequeued at most once. Okay. So a node throughout all the process, all the iterations, a node is enqueued once and it will be dequeued once. Okay. The operations of enqueuing and dequeuing will be taking order of one time. Okay. So I'm enqueuing one node, I'm dequeuing one node. Okay. That will be taking order of one time. And so the total time devoted to queue operation is order of V. Okay. Total time. This queue operation. Because I'll be enqueuing one, dequeuing once. Okay. So the queue operations in isolation, if I am taking over all iterations, I'll be having, say, this is order of V. So if it is V equal to N, then it is order of N. And what I am doing whenever I am entering in this loop, okay, the procedure scans the adjacency list of each vertex only when the vertex is dequeued. So when the vertex is dequeued, so this you see U is dequeued, and at that time all of its adjacent vertices we are checking. Okay. It scans. So at that time what it will be doing? So mind you, we are telling that until and unless we are telling otherwise, we will be implementing the graph search or whatever algorithm we are discussing. We will be going through with adjacency list representation of the graph. Okay. So now it will scan each adjacency list at most once. Okay. So it is dequeued once a node. That means its adjacency list will be explode only once. Okay. So it is never being enqueued again, right? So there is no possibility that another time in the whole iteration, another time I'll be dequeuing that guy again, and then I'll be exploring its adjacency list. That means its adjacent vertices. Okay. So this we are having one node. It is dequeued once, so that means its adjacent vertices will be, that means its adjacency list will be explored once. Okay, right? Its adjacency list. Now, since the sum of the lengths of all the adjacency lists is order of E, okay. So if I am having this guy, okay. If I am having this guy, his adjacency list is this, having these edges, okay, right? And whenever I am having this guy, its adjacency list is having only one edge. This guy, its adjacency list will be having this and this. Okay. And whenever I am having this guy, its adjacency list will be having only one edge. Okay. So for each node, I am checking its adjacency list once. So if I add up all these edges, say its adjacency, say this its adjacency list, how many edges will be having? This guy say 1, 2, 3, 4, 5. One having how many adjacency, uh, uh, how many number of nodes or how many number of edges this guy will be having as its adjacency list? 3. So this 2, 2, 1, 3, 2, then 4, 1, then 5, 5, 5 only 1. Okay. Is it? 5 is 1. So how many such? How many total? 8. How many edges in the graph we are having? 4 edges. So you see, whenever I am counting this guy, this edge is coming. Whenever I am counting this guy, this edge is coming. So that means double count. So if I sum up all the adjacency list, its edges, what it could be at most? Twice of this E. Twice of this E. So twice of this E. It will be less equal to this. Okay? Are you getting? It could be at most this. So that means if I sum up all the adjacency list, so I am taking in the graph, I am taking in the graph I am taking in the graph each node its adjacency list will be explored once. Okay. So if I consider all nodes I am exploring one by one, then how many edges I'll be exploring in total? So it will be the sum of the adjacency list, because one node, its adjacency list I am checking. That means what are the edges it is connected with. If I sum up all these nodes, edges, then it will be what? It will not be crossing less equal to 2e. That means order of e. Order of e number of edges. Order of e number of edges we have to scan. Okay. So the total time spent in scanning adjacency list is order of e. Okay. Because it will not be crossing this 2e bar. Okay. So the in this thing in this looping process, what is the bulk of the checking I am doing? The adjacency list I am exploring. Okay, and total of this is order of e. Okay, the total of this, and the overhead of initialization is in this part we have got order of v. Okay, right, and in this part we are having order of e. Okay, so the total uh, time complexity, the total running time of BFS procedure will be order of V plus E. Okay, that means order of V plus order of E, and we can write that in this way: order of V plus E. Okay, so this is the way we analyze this BFS. So one algorithm I have done, and the rest of the algorithms you will be doing in your hostel. Okay, and the rest of the algorithms almost with the similar analysis, it will be similar analysis will be doing the trick. Okay, so this is for breadth first search, and now we can go for this DFS. So this DFS having nice nice little application in this maze exploration. Okay. So you are here, and you have to go here. Okay. So then you can come like this. Okay. So this way you can go. Okay. And eventually maybe you will be reaching, or at some point of time you will stuck, and then you have to come back again, and then you have to search. Okay. So what this BFS will be doing, say it is going deeper and deeper, and then it is stuck here, and then it will be coming here, say it will be coming here, then it will start exploring from here to here, and then it is stuck here, then it is coming back here, say then it will be coming here, say it will explore this, then it will come back here, say, and then it will explore some other edges, then it will be coming here, then it will be coming here, so it will explore its other edges, something like this, and maybe this is the guy I'm looking for. Okay, so this thing we can so This is the graph. This is a maze graph, say. Maze pattern we are having. And here this vertex we can represent as the intersection, and edge may be represented as the passage. So this is our intersection. Okay. These are some kind of intersection. Okay. And these are the passage. Okay. So this is some, maybe here, okay, maybe here, right? And we are having some kind of passage here, so we can have one edge. We can have one edge here. This is a one passage. We can have an edge here, and this is one passage between these two nodes. We can have this connection. So this is the way they are transferring this maze into this graph. Okay. So can you convert this into this graph? Okay, and then whether from here whether you can reach here or not, by having this breadth first search, running breadth first search on this graph, you can determine. Okay. You can determine that whether you can reach from here to here. So that is one application of this depth first search. So this maze is a little bit complicated. Okay, so this you should follow this Sedgwick video regarding this. Okay. Another application of this depth first search is this flood fill or blob fill. Okay. Now you have gone to paint. Okay, right? Paint. That is the drawing software, right? And you have selected some portion, say some portion like this. Say some portion like this. You have selected with your mouse, and then you have given one color. You have picked one color, and then all of a sudden you will be seeing that portion is colored green or red, whatever you have picked up. Okay. So this happens many a times. Whenever you run any this GUI based application, you are having this kind of thing, say Photoshop or whatever. Okay. Say GIMP. Now, actually, what is done? Inside, in the background, we run this DFS algorithm. Okay. Right. So each individual, so this picture is nothing but the collection of pixels. Right. So this picture is nothing but some collection of pixels. Okay. The more pixel you will be having, say if I am having these pixels, this pixel representing this picture. If I am doing this, then it will be a little bit blur. Okay. So the more pixel you can arrange, the more resolution of this picture you will be having. Okay. So this, whenever you are selecting some area, say this area you are selecting. So inside we can think that this grid is becoming formed. This grid graph is formed, which is joining each pixel like this. And then you run this DFS algorithm. Okay. DFS algorithm, and then you start coloring this pixel with red, this pixel with red, this pixel with red. So eventually all the area will be colored as the desired color you want. Okay, whether it is white or gray or red or green, whatever. Okay, so can BFS be implemented? Can we implement this flat fill with BFS? You think of, okay, in your hostel. So you see this breadth first search and depth first search, it is having plenty of applications, right? Plenty. And maybe it is plaguing. We are unknowingly, we are not aware about this. We are absolutely not aware. Okay. So both of you, both these algorithms you should implement. So maybe you are having a grid graph like this. Okay. You imagine that that is coming from that image. Okay. And then you run this DFS after understanding the DFS algorithm. Okay. And then this maze. Okay. Now we are going to this step first. Okay. So today up to this.